Good morning, ladies and gentlemen.
What have you got there, Miss Mo?
So I have a stopper at the end of my string, and I have a paper clip on this end, and a string that is threaded through this this pipe here. And what happens is if I pull this way, I can shorten the length between this point and the stopper, and I can make it go long.
So what?
Okay, so what? Okay, so I'm gonna go ahead and I'm gonna go start moving this thing around in a circle like this.
You see that going around? Yes, you can.
Okay, now I'm gonna go ahead and start.
Whoa. Look how fast it goes.
And what's going on here?
Why does it do that?
Why does it do that? And that is gonna be the goal of today's lesson. We're gonna talk about why does it do that? What's going on here? Okay, so momentum we know is mass times velocity.
We spent a whole unit on that.
Exciting stuff. And then angular momentum. Momentum for angular dynamics is represented by L. And then this is basically mass times velocity, parallel universes. But this is moment of inertia and angular velocity.
Angular velocity, that's right.
By omega. Okay, so let's imagine that we have two disks that are rotating independently around the same axis.
Okay.
Axis, disk 1, disk 2. My first question for you is, what is the angular momentum of a disk with a moment of inertia of 3.4 kilogram meter squared and a angular velocity of a positive 7.2 radians per second?
Go ahead, boys and girls. I don't think you're going to find that this is too hard.
3.4 times positive 7.2.
I didn't put this on the tripod.
Oh.
It's okay. That's all right.
Do you want to?
No.
Oh, here we go.
I'll make do.
I will survive. Okay, 3.4 times 7.2. And I get 24, we'll call it 24.5.
24.5 kilograms meters squared per second.
Meters squared per second. Ooh, okay, so that was for A.
Yeah.
Let's go ahead and take a look at B. So this is our second disk. Again, these disks are both rotating around the same axis. What is the the angular momentum of a disk with a moment of inertia of 4.4 kilograms meters squared and a angular velocity of a negative 9.8 radians?
What does that negative mean?
That just means one is going counterclockwise and this one is going clockwise.
Or vice versa.
Is that mix those up?
I can't.
I remember them being opposite of what I would think they would be. Okay, this one is negative 43.1.
Hey, boys and girls, ¿quién es más macho? Esto. Oh. Esto.
Kilograms meters squared per second. Okay, so
now we know their angular momentum.
Yeah, so this momenta. One is the greater one. If these two disks are linked together with no external torques, so that they are rotating together as a single unit, what would be their final angular velocity? Well, this is a collision.
A collision.
So think about it. So we have disk A that is going this way, and then we've got disk B that's going this way. It has a bigger, I'm trying to draw a little of a scale. Okay. Yeah. And this is before. And then after, when they are put together, we view them like this, A and B, and they're going that way.
Yeah.
Right?
It's kind of like a collision with linear motion, which is kind of what we've got drawn here, but it's exactly the same idea.
Yeah, same idea. Okay, so let's review. A system is a defined set of objects in the energy associated with them.
Yep.
Internal forces. these are exerted by the objects on each other.
That are part of the system. Yep.
Part of the system. Newton's third law says these sum to 0, equal and opposite. External forces come from outside the system. In an isolated system, external forces sum to 0.
Yep.
Okay, conservation of linear momentum. You have seen this before. The total momentum of a closed, isolated system is constant. The momentum in the beginning equals the momentum after. Total.
They don't change, yeah.
Don't change. So if I asked you if a 2 kilogram ball rolling at 4 meters per second strikes a stationary 2 kilogram ball, the original ball is stopped dead in its tracks. How fast does the second ball roll away? Well, if momentum is conserved, it's got to be the same velocity, right?
They both have the same mass, so the momentum before is going to be 2 times 4, which is 8 kilograms meters per second. The momentum afterwards is going to be 8 kilograms meters per second. And since the first ball is stopped, all the momentum's in the second ball.
Transferred.
Remember doing this stuff?
If you don't believe us, do it the long way out, write it all out, and you're going to get the right answer.
That's right, that's right.
Okay. All right. Conservation of angular momentum.
Yeah.
The total momentum of a closed isolated system is constant. Didn't we just basically?
That sounds like exactly the same thing. We just have a different symbol here.
Yeah. So this is parallel to momentum here. The angular momentum total before is equal to the angular momentum total after.
That's a prime. That's the best Mr. Boykin could do.
And so, if these two disks are linked together with no external torque so that they are rotating together as a single unit, what would be their final angular velocity?
Now this thing at the bottom here shows that the moments of inertia add just like masses do. You got one plus the other, you add them together, that's the total. So what are we going to do with this?
Well, should I erase this then?
You need that information. Let's see. I'm looking what's coming next. Oh yeah. You know what I would do is I'd lift the thing.
There we go. Oh, I forgot to erase my stuff from before. Oh my gosh, this is from
Zero momentum frame.
Yeah.
Wow.
Okay, so
perfect.
how are we gonna look at this? Well, we know
L before is equal to L after.
right, and we know that
L1 plus L2.
oh yeah, L1 plus L. Oh, that's right here, right? This is like L1 plus L2 is gonna equal
L total.
the combination of both of them.
Yeah, because they're stuck together. Okay.
And so if we wanted to know, the question is asking what the angular velocity is. That's the omega, right?
That's the omega. So what is L?
Well,
L1
L
is going to be I1.
moment of inertia. Do you want to put this in here too then?
Yep, I1.
Okay. Plus I2 omega 2 equals it's going to be I
1 plus 2.
1 plus 2 omega
Final.
Yeah, I was like, not 1 plus 2. So 1 plus 2 here, because the masses are going to add together just like our masses. We could also say like moment of inertia final. That's what we do.
So boys and girls, see where we just have letters? Don't put any numbers yet. Let's solve this for the final angular velocity.
Yeah.
With no letters, just numbers.
Okay, so these cancel. Now, don't we have this information over there?
Yep.
Okay, one is this one.
It's
is this one, right?
Yeah, 7.2 radians, I beg your pardon, 24.5 kilograms meters squared.
Plus, what is it, negative 43?
Negative 43.
0.1 kilograms meters squared per second. And that's all over the masses, the moment of inertias of both of them.
So it's 3.4 plus 4.4.
4.4 kilograms meters
Squared.
not S for squared. Squared.
Yeah.
Kilograms meters squared. Okay, so we can do this.
Can you put that in your calculator, boys and girls? You're going to have to put parentheses around the bottom.
Okay, so I'm gonna do 24.5. Oh, it's not on. Okay.
Works much better that way. Huh?
Sure not. 24.5 plus a negative 43.1, and then I'm gonna divide by parentheses, like Boykin said, 3.4 plus 4.4, and then I get no squared, nothing. I get 18. Let's call it 19.
Negative or positive?
I have a positive number. But that doesn't make sense, right? Because
No, it should be negative.
You know what? You know what I'm going to do? I'm going to put the top part in parentheses. 24.5.
Oh, yes, you're right. Oh, yeah.
Plus a negative 43. Good catch, Boykin. I was like, 19. We're done.
Well, that's like why I asked, ¿Quién es más macho? And it's B is más macho.
Plus 4.4. Okay, that's more like it. I get a negative 2.3. We'll call it negative 2.4. That's a more negative 2.4. It's kind of slow.
Well,
Oh,
you know,
yeah, 'cause
it's
they're
like after the
going the opposite
collision,
direction.
there's some cancellation taking place.
Okay, let's talk about what we did here. So, trash can down.
Down goes the trash can.
So, initially, we just wanted to calculate the angular momentum of disk A moving in its direction.
Yeah.
And then we wanted to calculate the angular momentum of B moving in its direction. Now, what happened is we like superimposed those on top of each other.
They had a collision.
Rotating around the same axis. They had a collision. And so before they were separate, now they're together. We have to think about the conservation of angular momentum.
And use the pyramid rules.
Yeah, one thing that Boykin and I have been noticing on your tests is that you're plugging in the numbers way too early.
Yeah, and making mistakes.
Yeah, and making mistakes. It's easy to make mistakes when you've got all these numbers to put in there. So start with angular momentum before, angular momentum after.
Because something might be
Break it
0,
down.
you could make it simpler.
Exactly. All right. So once you get this part down, in fact, I think we gave people points when they had this on there, right?
That's right.
We totally did. Okay. I'm probably gonna forget about this and erase it in 2 weeks. Oh, let's refer down there. Okay. All right. Oh, YouTube video. I forgot to cue this one up.
Should we pause this?
We can pause it.
All right, pause. Play.
Okay, here is our video.
Hey there. This video will be explaining the physics behind spins in figure skating. If you have not yet seen my physics in figure skating jumps video, please see that one before this one, since there are some concepts that I will be reusing in here.
Can't see anything.
Here is a backspin. A backspin is done on the right leg if you are right-handed, and the rotation is counterclockwise. Spins generally finish in a landing position, just like in jumps. Let's begin with how a spin starts. As you can see, I've already generated angular momentum even before I started spinning by skating on a curve and by pushing with my other leg. So now that that's covered, you may be wondering how I went from skating on a curve to spinning so quickly. This is also down to angular momentum. You may remember L equals I omega from the jumps video. This does also apply to spins, but not this part of the spin.
Yeah, it does.
For this part of the spin, you need to know this other angular momentum equation. L equals R times M times V, where L is the angular
Just
momentum,
kind of ignore this
R
part.
is the distance from the mass to the rotating axis, M is the mass, and V is the velocity.
This is when she's going around a
Part of
circle.
how I start spinning
Right
is in my
here.
foot. My left foot turns so that I'm no longer
She's going in a
moving
circle.
forward, and the circle I'm skating in is much, much smaller. The other part is where the zoo equation comes into play. At the beginning, I skate in a large circle so that R is large. Then, when I skate in a smaller circle, R is smaller. Now going back to that equation, because of the law of angular momentum conservation, if R is less, M is constant because your mass doesn't change, and angular momentum is conserved because of the law, then velocity must increase. Now that you know how a spin starts, you might wonder what happens in a spin.
This is the important
Well,
part.
the answer to that is quite simple. It's really the same as when you rotate in a jump. So that means that you can increase the speed of the spin because of the moment of inertia and the conservation of angular momentum. Just to clarify, the equation for angular momentum when starting a spin is L equals R and V.
Ignore that.
Ignore the top one.
All right, go
And
ahead.
the equation for when you're rotating in a spin or jump is L equals I omega.
That's what she's twirling.
Next up, change of position and change of foot in a spin. Here you have a combination
Look
spin
how-
of 3 positions, 2 on one leg and 1 on the other.
Notice how she goes faster and then slower.
Did you notice how my speed increased when I went from the first
Where's the
position to
axis of
second?
rotation?
Well, that's down to the moment of inertia. In the first position, the distance from the mass to the rotating axis is much greater than in the second position. So that means that the moment of inertia is less in the second position. If the moment of inertia is less, then the angular velocity is greater.
That's because the angular momentum is the same in both
Finally, the
times.
change of foot. You may also have noticed that my speed increased after I changed feet.
She's
Yes,
just
it is
showing
also
off.
because the distance from the mass to the rotating axis is less, but that's not all. If you look closely, you'll notice that my left leg pushes on the ice while my right toe pick is anchored in one spot.
Cheater.
This additional force allows me to increase the speed of my spin.
Because friction is slowing her
This is
down.
basically the physics behind spins in figure skating. I hope you enjoyed this video, and of course, I hope you learned something too.
I loved watching me and my mom would always watch the ice skating Olympics. Okay, I'm gonna close that one. Okay, so I'm gonna go right along to this next one. Oh, actually, you know what, Boykin, should we do the whole thing on the board with the I's and the W's and the bigger and the smaller, or should we wait for that?
We'll do it right after this.
Okay. All right, so this one says, why does she spin faster? Here we go.
And this is the world record figure skating spin. World record, boys and girls.
Here it is. Put your hands together, ladies and gentlemen, for...
Some Russian woman. Big eye.
Oh!
Wow! 300 Natalia Kononuk. Let's see that again. Let's see that bad boy again. Big eye. Small eye.
What's changing?
Holy snap.
What's the same? What is changing? Okay.
That's a great question.
I think we're gonna do this. We're gonna do this one first, actually.
Yeah.
Okay. All right. So this is her final. What was it? Caitlin Van.
She was, Natalia Vinokurova, some Russian name. So how can we go from revolutions per minute to radians per second?
Okay. Well, we can just.
You want to get rid of the revs or the minutes first?
Let's get the revolutions out of there. 1 revolution is equal to 2 pi radians. Yes.
Yep.
Okay. So that cancels those. Oh, I don't need the equal sign yet. Gotta get rid of minutes.
1 minute. It's over 60 seconds.
Okay, and now our minutes cancel. We've got radians per second. Okay, so 308 times 2 pi, divided by 60, and I get 32.3.
32.3 radians per second. All right, that's her final angular velocity, 32.3, which is hella fast.
That is so fast. Okay.
But her starting, she went around once in 0.63 seconds.
How did you know it was once, Boykin?
I watched the video with a stopwatch.
2 pi is one revolution.
2
right?
pi is going around once in 0.63 seconds.
So I'm just gonna do 2 pi divided by 0.63. And I get 9.97. Okay, 9.97
radians per second.
radians.
So when she skated into that big circle, her angular velocity was 9.97. When she pulled everything in tight and was spinning around in a blur, it was 32.3 radians per second. So that's stuff that we can measure, that's stuff that we can know.
Okay, now my next question says, what is the ratio of eye to eye? And you know what? Oh no, I guess I can.
You want to do the big and the little?
Let's figure out what the ratio is first. You know that.
Okay, I like that.
Yeah. I remember we're like, are we ready yet? Are we ready yet? Okay, so what does it say up here? It says this, right?
See, we can't know what her moment of inertia is. We can measure this, but we don't know. All we know is that this is smaller than this.
But you said something really important earlier. How come we can't know exactly what this is? Before we had like 1/2 mr squared, 1/10 mr squared.
Yeah, in the book there is that whole
That
column
list, right?
of different moments of inertia for regular objects, but for humans we got mass distributed everywhere.
We're not a regular object.
That's right.
Okay, so we have our law of conservation of angular momentum. That is this equals this, right?
So if we want this on top and this on the bottom,
let's just go ahead and divide by this.
okay,
Those
now
cancel.
what do we do with the angular velocity?
Put it over here.
So the
now-
ratio is going to be the angular velocity afterwards divided by the angular velocity before.
Which is 32.3 radians per second divided by, you know what, let's call this 10.
Yeah.
10 radians per second. Miss Morse is being lazy.
That's going to be 3.23. And there's no units.
no,
It's a
there's not.
ratio.
I was gonna say, look,
So that
cancel.
means that when she's all out there with her feet and her arms spread wide, she's 3.23 more moment of inertia
Let me get rid of that, yeah.
than when she sucks everything in.
Okay, so why is that? Now this is the why. I'm gonna erase this. I can erase it all, right?
Yeah.
don't think
It's
we
like
need to
when
explain.
she had this and the string was long, it went slow.
Oh, good.
And then as she pulled the string in.
Should we do it one more time?
Oh, let's do it
Let's do it
again.
again.
What the hell?
Okay, so it's just like this. Okay, so the lady, the national champion, what is she, the Olympic champion? Whatever.
Yeah, she's
Okay.
hella big.
When she first goes into her spin with her leg out,
She's going around slow.
okay, and then she brings it all in tight. She goes, whoa, faster. Get a little nervous there. And what's changing? Well, the radius here.
And what's staying the same?
Her,
Angular momentum.
the angular
Angular momentum before is equal to the angular momentum afterwards.
So,
And so before we have a big I and a small omega, and afterwards we have a small I and a big omega.
going fast, going slow in terms of angular speed.
Yeah.
And what is this made up of?
That's mass times the radius squared. For the stopper on a string,
And over here, we have the same
Same
size
mass.
mass, but this time our radius is a lot smaller,
that's right.
okay? And notice how, since this is really big, this has to be small to keep this equal to this. Over here, now this is smaller, this has to be big. These two things, they have to equal. This is conserved.
Put an equal sign in that bottom
Oh,
line.
thank you. So there has to be, they have to kind of balance each other out to make it
What
work.
else do you notice, boys and girls, about this equation? Besides the size of the symbols. Do we have anything the same on both sides?
Oh.
Boom, ba boom, ba boom. Woohoo!
So, do those cancel out then? Is that how it works?
It does.
Okay.
Mathematics rules the universe.
Okay. Wait, let me go back. Is this our last one? Oh,
This is
no,
the
it
last
Okay.
one.
Okay, so we will leave you with this.
And this is going to be part of the homework. I love these things. University of Michigan Physics Demonstration Lab presents 1Q40.75. You guys seen these things before? Coin launcher with a penny. Boom. Your coin's gone. Angular momentum is the same. The radius is changing. Let's go back and see that again.
Who's counting it? Okay, ready for it. This is why I lost all my
Now what
at the
yeah.
museum.
What happens, the launcher launches it tangent to the circle. It has a certain amount of angular momentum there. That angular momentum stays the same, but notice the R is getting smaller. The radius of rotation and the angular velocity increases, just like cool. All right.
Okay. So now
I think that's it.
that is it. What was our homework going to be? Our homework is going to be right here. I forgot to put it on there. But here it is in all of its glory. You guys are going to answer this question, and ice skater questions, and then merry-go-round question, and then this is a coin is launched into a coin funnel. And we might have another question on there for you guys, but here's the homework. You guys know what to do. Use what you learned today. Rock and roll.